Where does chemical waste go once we're done with it in the lab? What does it take to actually make chemicals, and what's its environmental impact?
The most important consideration in making chemistry greener is what it takes to make reagents and solvents all the way through the industrial chain, from extraction of materials to delivery at the lab. The major precursor of sulfuric acid, for example, is mineral sulfur, which is extracted from open-face mining, which destroys the landscape and leaches pollutants into the environment. The purified sulfur is then oxidized in what's called the contact process, which releases toxic acidifying pollutants at an alarming rate into the environment. Despite this, even when we use it catalytically, we tend to pour it down the drain, which creates an increased demand for this whole unsustainable polluting process. As another example, one of the most recyclable materials we use in the lab are organic solvents, derived from fossil fuel, and are therefore really unsustainable. Solvents can be recycled and reused by simple distillation, which would thereby decrease the demand for the petrochemical precursors involved in their manufacture. One of the most exciting reactions students get to perform in 213 is the Grignard reaction between bromobenzene and benzophenone. This reaction is water sensitive and requires students to fine-tune their experimental skills for it to work. We usually use diethyl ether as a solvent, which is generally all lost during rotary evaporation. 50 mLs per student doesn't seem like a lot, but for a class size of around 20 people, it adds up to about a liter of unrecycled solvent. During research, we actually came across a sustainable alternative to diethyl ether called 2-methyl-THF, which is derived from biomass left over from agriculture. We use this in place of common ether in the 213 Grignard reaction with excellent results. We actually obtained a greater yield with this high boiling point solvent. The lower vapor pressure of the solvent actually allowed us to recover around 50% of the solvent by rotary evaporation. Gas chromatography showed us that the recycled solvent was almost pure with still some water present. With just a little bit of tweaking, we could reduce the environmental impact of our laboratory while taking the opportunity to teach the ethos of green chemistry to future generations of pharmaceutical and industrial chemists that come through our undergraduate lab. If we don't start gradual changes now, the compounding effects of industrial emissions and pollutants will irreversibly change our climate and biome, ushering in an era of mass extinction and catastrophe.